last week, and my decades-old computer didn't like that. Okay, so this is not the right lab. There we go. Get that out of here. Okay, so what is going on in this lab? We have kind of a translation between what is known as a linear quantity, which is like position, velocity, acceleration, and their corresponding angular quantities. So we're going to use a little bit of trigonometry to understand how to go back and forth between the two of those systems. It's kind of like a little dictionary. And so this background, kind of like the very first equation, they start off with this thing which is kind of hard to understand, and they actually work backwards. So I'm going to do the opposite direction. I'm going to show you how to get this formula before we do anything. Well, actually, I'm going to start with this because that's kind of the most important. That's like a dictionary. So let's start off, and we're going to think about a linear quantity like position, and think about how that can be transformed to something in an angular quantity. So we can remember, so throughout a lot of this intro, I'm going to be like citing because trigonometry, but I'm not gonna go through it because it would be 30 minutes longer if I reminded everyone and myself about what a lot of the things we did, and maybe like geometry or something in like sophomore or junior year of high school. So I'm just gonna kind of skip that and say, we can find it on Wikipedia if we want. But here's kind of this formula that you might remember for arc length. So it says that if you have a circle of radius r, and this kind of vector or arm or whatever sweeps out an angle of theta, the length that it subtends or sustends or something like that, some kind of word like that, the area that it covers or length that it covers is, I don't know why I called it S here, and I like L better. So L is r, this radius, times this angle that it sweeps out. We are actually going to be concerned with that angle theta, because it turns out this is a linear quantity and this is an angular quantity. So to get from one to the other, what we end up doing is dividing by the radius. So that's kind of the main takeaway of when you go back and forth between linear and angular quantities. This is like a dictionary, like English and Spanish or something. And the formula to get from one to the other is dividing by r. So theta is this distance here, and in order to go from a linear to an angular, we divide by r. Same thing for velocity. Velocity in angular, which we'll call omega, that's that little Greek symbol omega, is v divided by r. It's also just like v is the derivative of L, the time derivative of L. Omega is the time derivative of theta. Same thing for acceleration. So acceleration is the derivative of velocity. Velocity is the derivative of position. And the same correspondence here holds. Now we're going to get into a little bit more trigonometry. We're going to think about an object spinning in a circle. So for instance, it has like a velocity as it's like, for instance, I can do what we're going to be doing in lab. As I'm spinning this thing around, if I cut the string, so for instance, if even the planet or the planet and the sun, if I were to cut this string right now, it would go flying off straight into the direction that it was. So for instance, if it's coming around this way and I cut it, it's going to fly in a kind of a tangential direction. So that's what I mean when I draw these velocities. Like, imagine the thing is spinning in this direction, and I cut the string and it just flies off in the same direction that it was going. So what I'm going to do is I'm going to start using these things called similar triangles. I'm going to draw these vectors. So one vector pointing up, one vector pointing, a little bit to the left and up. I'm going to draw a triangle between, or I'm going to draw two vectors, and I'm going to define this thing dv, which I should have defined on that slide, but it's over here somewhere, right here. So dv is just the difference between the two. So for instance, if you have this formula from geometry in high school, also remember difference of vectors. It's like it would be the arrow pointing from one to the other. So like that. So x would be b minus a, like this. So if a is pointing in that direction, b is pointing in that direction, a minus b is an arrow that points from b to a, like that. So our dv points here from v1 to v2. So I have this kind of triangle here. The biggest assumption that we're going to make is that this triangle, actually, let me back up a second. A little bit smaller assumption is that when I think about acceleration, because right now what I'm doing is I'm trying to derive this formula. This is another word for centripetal. You can just call it angular. So what is the angular acceleration when something is traveling in a circle? And so that's what I'm trying to find. I know that the definition of acceleration in the linear world is just dv dt. I'm going to make this assumption, which tells me that I'm not only looking at super small quantities, but kind of big quantities, depending on how big my circle is. And then I'm going to use the geometry that I have, which is that if my circle is large enough, I can assume that even though this thing is curved, so this L, right, it's a circle, it's like a pizza slice. But if it's big enough, or actually, I'm sorry, if it's small enough, I can assume it's kind of like this. So it's kind of this, I mean, this is kind of, almost the flat earth argument, right? Like you can't really tell if this is a small enough area that the earth is round, everything looks kind of flat. But here, we're going to use this assumption. We're going to assume that this arc angle L is small. And again, by trigonometry, I'm not going to prove it, but by trigonometry, this angle between the two vectors here is exactly equal to that vector here. So you can either prove that rigorously, back in sophomore or junior year of high school in geometry class, or you can just you can believe it for now. We can kind of guess if we were to bring this down and keep drawing it downwards. That's kind of the triangle that we make. And likewise, if we do for this one and go along it, that's the same square, actually. So that kind of justifies that if you cut the square in half, either way, right? You cut it this way or you cut it this way, that angle's the same in either of them. Okay, that is actually helpful. I forgot to mention that yesterday, the little square argument. Okay, so now that we have this relationship, that these two triangles are roughly equivalent, now I'm going to look at some ratios, because I know over here that this quantity is important. So I'm going to look at that quantity, L over R, and I'm going to make the same quantity. So if this is L over R, this is dV over V. Then I'm going to rearrange some things, because this I know I can plug into this one. So I want that quantity. I'm going to rearrange. I put the V over here, and I have this L over R. The next thing I'm going to assume is that as my thingy is traveling around in a circle, I'm going to make the assumption that this length that it travels is really just the velocity of whatever it's moving. So because I assumed that it's not, right, I looked at such a small, where is it? This one. Because I did this kind of flat earth argument that the slice I'm looking at is so short that it might as well be a straight line. Well, I know that the straight line is moving with a velocity v. V is kind of like the average of both of these things. I'm assuming that it's just kind of going around in a circle with the same speed. So I can also write L as, where is it? The velocity that it's moving with, the linear one, and the time it takes. So this is like a time interval, like 1 second. So it's moving at 10 meters a second for 1 second. That means it moved 10 meters. And just a sanity check. This is a length. This is a length over a time, and this is a time. So those two things cancel, and it's a length. And so I'm going to plug in this equation for my L now. So I have V dt V over R. And then I plug into what I know is the acceleration, dv over dt, which now if I look over here, I have that. I have dv and I have dt. So if I bring this down into the denominator of the other side, I have v squared over r. So v squared over r is exactly the centripetal acceleration, or the angular acceleration, really. You can think of those two things as equivalent. I think it helps when you think about like this kind of dictionary here. And the only other thing that they're doing in this step right here is they're writing things in terms of angular velocities instead of linear. So remember this conversion. We can reverse this. So like what is V in terms of omega? V is omega times R. So if I bring this R up here, it's V equals omega R. And so you can plug that in here, R omega squared, you get a R squared and an omega squared. The R squared over an R cancels, so you just get one R. So that's this part of it. And then because we know what force is mass times acceleration, then I'm just plugging this in. So F equals M omega squared R. And that's what they get here. Equivalently. Now, this is the same thing as this. Okay, so now let's talk a little bit about what our system is. Because this drawing was kind of confusing to me when I first stepped into the lab. So what is going on? Let me just do a short little demo here. This is done a little bit incorrectly, but this, for all intents and purposes, is fine, just tying it like that. But what you can also do, find another one. And also you can just come up here and grab washers from that one, because there are thousands of these little kits in here. So we have these washers, and this one is kind of set up with this, what they have in the picture, which I will go over here for. So you see this kind of like paper clip. So you can tie it anywhere to the paper clip, like, dirty, like that, up here. Okay. And then what you do is you can take your washers and slide them through the paper clip. So just maybe make the paper clip skinnier, like smushing it through the paper clip and through the washers. And then you can slide the string towards an area that's like kind of in the middle, like that. And then when you let go of your washers, they kind of sit on it like a swing. And so that's an easier, or you can just tie a bunch of knots and keep cutting, because the strings on these things are way too long. So they're super long. And then you have this cord clamp, which is kind of like a thing on a jacket. And this tube, it's like a pen tube or something like that. And then this stopper. And so what you do is, it's way too long. Stand up, show you how this works. Right. So I put on enough washers so that you can see this thing is not exactly at the end of the tube. So the first thing, like if you spin this really quickly, the I don't know, what do they call it, cord clamp will stay right at the tube. So that is not good, because now we're not getting any information. We can just keep swinging it and it doesn't matter. But you see, as soon as I stop swinging it, the tension of that, the weight, like this capital MG right here, is pulling more than the centripetal force is pulling here. So centripetal force is an arrow that's pointing this way, like out from the tube. And the tension, because it's a string, is pulling into the tube. So if these two things balance, that means the cord won't go anywhere, and this little jacket knob cord clamp will roughly stay in the same position. So what we want is I took like an inch. So that means for the whole lab, I focused on making sure my cord clamp stayed about an inch below my tube. And then what I did was I spun it so that that occurred. So right here, obviously it's not spinning, so the cord clamp goes down. As I spin, you can see that it raises, and I have to make it spin the exact right amount. Go slower, and you see that it's slowly falling down. And there we go. So it's about an inch, and then I pick up the speed again so that I maintain an inch. And then what we do is we time how long it takes for that thing to revolve around. Obviously, it would be quite hard to time one and then start and stop immediately, because that would be one period. That is what we want. We do want one period, but what we're going to do instead is time 10 periods. So you press the stopwatch 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you stop the stopwatch, and then that is 10 periods, which you can divide by 10 and get the actual period. So that is how the system works. And now, why does it work? There are actually two neat things that cancel out in the model, because if you can tell, when I was spinning this thing around, it wasn't doing this, right? This is like exactly a straight line. That would be ideal, but if you did that, it would, this thing would be up at the end of the tube and we're not getting any physics. So what actually happens is it kind of looked like this, right? Like a carousel or something. It wasn't a straight line, but all we know is that I don't know why that happened. The centripetal force is pushing outward. So what we're going to do is take the component that's pointing in this direction, so like the straight X direction, and we're going to take the component of the tension in that X direction. So what that does is it gives you two kind of canceling parts or factors of a cosine theta. So if we look at centripetal force, it's pushing outwards. We also know that this, like if we make a triangle with this thing like that, the radius that it's spinning around is not the length of the string. So if the radius is r, then the actual point that it's spinning is r cos theta, because we can make kind of like a little, if this is the angle right here, we can make that, and then this, the bottom part right here that I'm pointing across with my finger, that would be the adjacent part, so that is the hypotenuse multiplied by cosine. And the same thing happens with the tension. So if the tension is pulling on this rope upwards, but it's actually, we want it to cancel. So our objective is to get this equals that. So the force and the centripetal force, the tension force and the centripetal force. But both of them pick up that cosine. So we have the tension force cosine and the centripetal force cosine. They both cancel. And so our equation that we're left with, which I think they should have written explicitly, because it's a bit confusing how they wrote it, is capital M, which you can see by this little diagram, is the mass of all the washers. So right, if you have 9 washers and each of the washers weigh 5 grams or something, then it's like a 45 gram big capital M, and then you multiply it by G. So that is the tension force. All the washers, the weight of the washers, the mass of the washers and the gravity. And then centripetal force is the mass of the stopper, which is this little like bathroom plug or whatever, the angular velocity squared, and the big R. So that would be, one of the ways that you can measure that, especially in part 3 of the lab. You want to make sure when you're measuring the radius that you're keeping in mind where you're measuring things from. So for instance, I chose an inch. So my whole objective for the lab was to make sure my cord clamp was about an inch below the tube as I'm spinning and counting. And so my radius is that. It's from the stopper to the top of the tube with the inch left over. And so that's my capital R. And now I have centripetal force. And so what I mean by this equation being kind of crappy, where is it? Pick it up like that. This one, I think this is kind of crappy. They should it makes it seem like this is what the tension force is, But what they just didn't expand it further. So the tension force is not like, yes, those two things are equal because that's the whole objective. It's the tension force and the centripetal force equaling out so that the cord clamp doesn't move anywhere. It doesn't go up or down. So yes, that's true, but it was confusing people a lot yesterday. So I wrote it out like the tension force is equal to the centripetal force. This is the centripetal force. This is the tension force. Let's see what is on this slide. Right, so the objective of the lab, scroll down to analysis. Well, let's see. Here you're measuring a bunch of washers. I didn't measure 16, so don't freak out if your value isn't like that. I just put a bunch of them on there and divided. Let's see. Yeah, so I put 6 on there. And the mass of the stopper is just this black sub thingy. And then you're getting a bunch of values. It doesn't matter what mass you put on, right? Like I did 6 washers. It doesn't matter. What I would recommend is that you skip 3. It tells you to do 3 through 15. I would not do 3. If you want to do 5 trials, you can do like 6 through 18. But just 3 was impossible to measure because it just spins so fast. Like it's the periods for 3 washers was like that, and like I don't know how to, even though it's 10 periods, I couldn't even see it. So you can start with 6. I would recommend. So yeah, just finding those things, finding the average, and then you're using equation 4 from the error manual to get your uncertainty in measurements. And then for the whole rest of lab, you're going to use that for your 10T so that you don't have to do it anymore. That's not what I meant to do. And then, propagating error from this. If you have 10T, you divide by 10 to get the period. You divide by 10 to get the uncertainty. Frequency is defined as 1 over the period. Should be, that's not what I wanted. Here, frequency is divided by 1 over the period. And we know that the angular, where is it? Right here. If 1 over the period is frequency, then the angular frequency, this guy, angular velocity, is 2 pi times the frequency. And remember, 2 pi is written like that weird, or you can just write 3.14, it doesn't really matter. But that's a little weird part of it. Also, there is a special, I had written this as equation 11, but there's actually a special equation right below equation 11. I don't know why it's not there. But the equation 12 is actually just a special case of 11. So for instance, if I were to plug in n equals -1 right here, this would be -1, which is just 1, it's the absolute value. And -1 minus 1 is a -2. So that just goes in the denominator, and then that's in the numerator. So these two things are the same. It's just n equals -1 to 12. That's just a shortcut. Okay. And then here, well, I'll get to that in a second. Is there anything else? Radius, you're measuring with your eyeball. One thing to note is that you should, the units of things really don't matter. Grams, yeah, grams, seconds, that doesn't matter because you're making a plot of it anyway. But the radius does need to be in meters because you can see up here that we're using gravity in meters. So when you're measuring distances, make sure to do meters. Let's see, hanging mass is just the number, whatever number of washer you use times the weight of, or the mass of one of the washers. And then the tension force is, remember, capital M times G. So capital M is hanging mass, G is gravity. So then the tension force is capital M times that. And here, let me explain what they mean by expected slope. So they're asking you to make these weird plots. They're asking you to plot the centripetal force. Actually, like, again, they're kind of messing up these labelings. They're quite annoying. It's tension. Tension. You don't have centripetal force at this point in the lab. So what they're meaning when they say make a plot of FC versus the mega squared is make a plot of FT, this column, and omega squared. You don't, if you notice, like throughout this whole, there's no FC throughout the whole thing. They're just like, in theory, what they say is true because, where is it? FT does equal FC. It's just, it's annoying that they don't, like, you know, it's confusing to students. Anyway, so you're plotting these two things. And so if we look up at our equation here, what does this, what does this mean? So if we want to plot this versus this, we have to rearrange this equation to make it look a little bit more like what we're familiar with, which is y equals mx. So I'm going to rearrange this thing. I'm going to bring my variable over here and my variable over here. So if I plot this on the y and this on the x, then my slope is the mass of the stopper and the radius of my thing. So that's what they mean by expected slope. They mean in the plotted slope, that means literally plot ft versus omega squared and get the actual value. Here, expected slope is what this value is, because we know these two things. We measured the mass of the stopper right here, and we measured the radius. So expected slope is just those two things multiplied together. And then you compare, do those two things equal each other? Same thing down here, just a lot more math. I don't know why they make you plot these two quantities. They're asking you to plot omega squared and 1 over r. So if we look at our equation, that doesn't look kind of anything like what we're doing here. So what we're going to do is try to get a 1 over r somewhere. So I'm going to divide both of these things by, or I'm going to kind of invert both of these sides. This is true because if I multiply ft over here and I multiply m omega squared r over here, it's the same equation, just backwards. And then I'm going to bring the m omega squared up to the numerator so that I can have a 1 over r. I know that I need that right here. And then I'm going to isolate this omega squared over here. Again, the whole objective here is to get it to look like y equals mx plus b. So now that I've divided this omega squared, I bring this ft over here and the m in the denominator. So now this thing is y equals mx, where I'm plotting omega squared on the y and 1 over r on the x. And then my slope is the tension force, which is capital M over G, capital M times G, divided by the stopper. So that's what they mean. A lot of people were confused by like expected slope versus plotted slope. Plotted slope is you literally make a plot of omega squared and 1 over r and see what it gives you. Whereas expected slope is you plug in the actual values that you have. Okay, that is it. We will get started. And questions? And all the discussion questions kind of suck at the end of the lab, so we're just not going to do them this week.